All right, we're going to continue on with our algebraic review. We're going to begin by talking about absolute value. You probably know that absolute value is of a number is its distance from zero. You kind of ignore the negative. It's just the positive part of that number. It's actually defined as a piecewise function. Now, what is a piecewise function? You've graphed and dealt with a little bit of piecewise functions in the past. We'll be dealing with them a fair amount in calculus this year. Piecewise functions are where you have different functions for different parts of the domain. Now, I don't know how you feel about piecewise functions, but you want to become more and more comfortable with them. As if this is an area for you that you really struggle, you might have me give you a couple extra problems that you can graph, or I can graph a problem and you can write what the function is and we can talk about it. So the definition of absolute value is right here. It says the absolute value of x is x if x is positive. In other words, the absolute value of x is just whatever is inside those little brackets as long as what's inside the brackets is greater than 0. And it's the opposite of that if it's less than 0. And that's because if it's the opposite of x, like -1, when we take the absolute value of -1, it's the opposite of -1 or +1. There are operations in calculus that we cannot do to absolute value, like take the derivative and take the antiderivative or the integral. So we're going to have to, when we do absolute value in calculus, sometimes we have to think of it as two different functions, either the positive piece or the negative piece. We'll be talking about this more again. All right, so how do you solve absolute value equations? Well, because absolute value equations do have two pieces, what you have to do is first isolate the absolute value. So the first thing you want to do is get the absolute value by itself. So this first example, the absolute value is right here, and it's not by itself. It has a -6. So I'm going to get the absolute value piece all by itself, and by moving the 6 over, and so now it looks a little bit more like our function right here. We have the absolute value of something equals 10 in this case. So what we're going to do is we're going to split it up into two pieces. And we're going to say that 4x plus 3 equals 10. That would give us an answer. And we solve this. And then we're also going to say 4x plus 3 equals -10. It doesn't. But if we were to take the absolute value of -10, it is +10. And so whenever I see absolute values, I think of this little thing right here because it kind of looks like the graph of an upside down absolute value. And so then I set it equal to the positive and the negative constant, and then we solve. So now I'm going to continue solving this, and I have two answers. Now I can always check those answers by plugging them in for x and seeing if I get a positive equation. Sometimes you might get extraneous solutions if your absolute value doesn't equal something that's a constant, if it equals something that has an x or a variable in it. And so it is good to check your answers on absolute values. All right, the next one is an absolute value inequality, and we treat it very much the same way. We want to get the absolute value part all by itself. So how do we get the absolute value of x minus 6 all by itself? We move the 3 over by subtracting it, so we get a 2, and then we divide by this 2 right here, so we end up getting greater than 1. Once again, we have two pieces. We have x minus 6 is greater than 1, and we have x minus 6. You notice how I left that? I'm going to flip my sign and make the constant negative. So those are my two pieces again. And now I go ahead and solve. This is x is greater than 7, and this is x is less than, and I add it +5. You know, I might make mistakes every once in a while, so if I do, you can please let me know. Say, hey, Miss Noodle, on the video, you added 5 and 3 and got 10, and tell me, and that way I can say, yes, you're right, I did, or try to correct it or something like that. Now, if I wanted to go graph the solution on a number line, I have x is less than 7 and x is greater than 5. In that case, x is greater than 7 is this graph, and then x is less than 5 is this graph. You remember how with absolute value equations, when you're putting the solutions on a number line, sometimes the arrows point towards each other and sometimes they point out. So in this case, every single answer that I've shaded is a solution. In other words, any number that's not between 5 and 7 is a solution. If your arrows point together, your solution is actually only the part where the arrows cross or mesh, or that they're both satisfied. All right, you need to know all of these parent functions. With your eyes closed when you're sleeping, if you break your arm, or even when you're not at school, I want you to know how to graph all of these functions. So I'm going to try to get rid of this a little bit so we can get down there. I think that you know all of them except for the bottom one, but I'm going to just briefly put these up on the board real quick. F of x equals c. That's just a constant, and so this looks a little bit like just a constant. It's just a horizontal line. The next one, f of x equals x. That is, whoops, wrong color. That graph is a line with a y-intercept of 0 and a slope of 1, so it looks a little bit like that. Sorry, it was supposed to go right through the origin and it didn't. We just talked about absolute value. That looks like a V. Looks like that. Y equals, or f of x equals x squared. That is a parabola. We should be parabola experts after Algebra 2 class. We hit parabolas so hard. F of x equals the square root of x. That guy looks like this. He looks like a parabola on its side, but only half of it. And yes, it has a restricted domain. Our f of x equals the square root of x is our first parent function so far that has a restricted domain. This guy, all of these first 1, 2, 3, 4 have a domain of all real numbers, but f of x equals the square root of x has a domain x is greater than or equal to 0. Let's see, this guy right here, f of x equals x cubed. He looks like this. And then f of x equals the cube root of x. It looks very similar, except for it's an inverse function, so it's on its side. So it's the same graph, but then on its side. What does f of x equals 1 over x looks like? That looks like that butterfly-looking thing, or I'm not sure what you guys, how you call it, but that looks like that. Also has a restricted domain. And then f of x equals b to the x. Those graphs can look different depending on if b is positive, if b is greater than 1 or less than 1. If b is greater than 1, we have growth. This is an exponential function. And if b is less than 1, we have decay, so it looks like that. Hopefully those are all reviews. You need to know all of those graphs, exactly what they look like, points on the graph, their domain, their range, etc. Just know them. Now the last function, may be new to you. It says f of x equals plus or minus the square root of r squared minus x squared. I'm doubting you know this one, so I'm going to go through where it comes from. You may remember from geometry that an equation of a circle is x squared plus y squared equals r squared. Well, if I solve for y, I'm going to square root both sides. Remember how when you square root you have to have plus or minus? I get this equation. So this is actually the equation for a circle. Now technically this is two equations. I have y equals the square root of r squared minus x squared, and then I also have y equals negative square root of r squared minus x squared. This green guy is the top part of the circle with a radius of r. So that's what this green graph is. It has a radius of r. And it's the top half of the circle. That's one equation. Since you have another equation, plus or minus, the bottom half of the circle would be like this. So depending on which piece they give you, whether it's the positive or the negative function, you're going to either have the top of the circle or the bottom of the circle. All right, you need to know all those parent functions. I believe that most of them are listed at some page on your book, and I can't remember that page right now. But they're in chapter 1. All right. How do you graph an inequality on the coordinate plane? The first one is a parabola, and I want you to begin by graphing y equals negative x squared plus 3. You may remember that greater than or equal to or less than or equal to are done with solid lines, and then if you have less than or greater than, they're done with dashed lines when you graph them. Right? I don't know if that rings a bell with you. Hopefully it does now. So we're going to graph y equals negative x squared plus 3, which means we're up 3, and then we are a parabola that's pointing down because it's negative. So the normal shape of a parabola is over 1, down 1, over 2, down 4. So I'm going to graph this parabola as good as I can. There's the line y equals negative x squared plus 3, but we don't want to graph y equals the negative x squared plus 3. We want to graph y as less than or equal to. Where are things less than the parabola? Things are less than the parabola below the parabola. So all of these points that I've shaded are our solution set. On this one right here, it's a line, and it doesn't have an or equal to. So when I graph this guy, I need to make sure and make it dashed. It's a line with a slope of 1/3 and a y-intercept of 4. So I go down here to 4, and I go up 1/3, up 1/3, up 1/3. And so it's going to look a little bit like this. What does it mean that it's dashed? It means that the line is not part of the solution. It's only everything infinitely close to the line. This time we're greater than, and so we would shade above all of these points that I just shaded. This one and 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 this one. All of these points are solutions. This one is not because it's not shaded. Where did my mouse go? All right, lines. Do you know what these terms mean? Would you know how to get started if the directions contain these lines? Intersection. Where do they intersect? Where the two lines are equal to each other. What does it mean to be parallel? It means their slopes are the same. How do you find the midpoint? You add the two x coordinates together and divide by 2. You add the two y points together and divide by 2. Do you know the difference between slope-intercept and point slope? Do you know the equations of those lines? This is y equals mx plus b. And this one is y minus y1 equals mx minus x1. Which one's your favorite? By the way, I'm telling you which one is your favorite, and it's this one. Okay, if it wasn't before, it is now. Point slope is your favorite. We're going to be using it all the time. And what does it mean that the two lines are perpendicular? It means that their slopes are opposite reciprocals. If you're not remembering how to graph lines, I know you didn't do it a lot in pre-calculus. It's something that we will be working with lines a lot because they are tangents and they have a lot to do with calculus, and we use them. So based on the review that we just did, you can add problems 15 through 18 and 20 and 21 to the problems you can do on your sheet. I'm going to keep going. We're going to finish up some trig things here today. All right, I will, or if I have not already, I will give you a sheet that's called Stuff You Need to Know Cold. It's kind of like the parent functions. By the time we take the AP exam in May, you need to know all this stuff without looking it up. One thing that you need to do is you need to know your unit circle. Know it well. If you didn't memorize it, bad idea. You need to memorize it now. What is the sine of 30 degrees? What is the cosine of 45 degrees? Where is 5 pi 6? Know your unit circle. I have a link to a unit circle on my website. It's even in color, and if you print it off, you can keep it in your notebook. You won't be able to use it for tests or quizzes, but what I did to help me memorize this is whenever I was in a meeting or somewhere where I wasn't exactly entertained to my potential, I would just draw the unit circle. I draw it over and over and over again until I remembered the unit circle. What graphs do you remember? Do you remember what sine looks like? Do you remember what cosine looks like? Tangent, secant, cosecant, cotangent. You need to draw all those. I would say that you need to be able to draw sine and cosine particularly well. You need to know tangent also. On the reciprocal functions, just be able to get to those within a step or two. If you need to go look those up, go do it. They can all be found very easily online. The following identities that are listed there need memorized. All of these do. So I'm going to give you a minute to look at them, write them down, start writing these as well. These are identities you need to have memorized. All right. Another identity that you were not asked to memorize last year, but you will need this year, more second semester is really when we'll hit this. They're called power-reducing identities. The reason that they're called power-reducing identities is because we go from a square down a power. So it was cosine squared and now it's cosine. You may think, oh, she's got a typo there. Sine squared changed into cosine. No, that's correct. Both the power-reducing identities are in terms of cosine. And yes, it's cosine of 2x. And I hope you realize that there's an enormous difference between the cosine of 2x and 2 cosine of x. These two are not the same at all. They're not the same as cosine squared of x. All of these mean different things. So if you're not sure, like, whoa, why is that different? Talk to me about that in class. Inverse trig functions. So we write those like this. We write sine inverse of x, we write tangent inverse of x, and we have cosine inverse. We have all of those trig functions. Let's talk about the domain and range restrictions for inverse trig functions in class. The reason that you need to know the domain and range of inverse trig functions is because there's a difference between asking this question, let me just pick that one, versus this question. Whoops. Did I write that? Oh, nope, I didn't write that right. Let me correct this. Okay, this question right here, the first one is saying, where is cosine a half? Well, cosine is a half in infinitely many places. Cosine looks like this, right? Isn't it a half over and over and over and over and over again? I'm not hitting the graph correctly. Cosine is a half. Think about the unit circle. Where is cosine a half? Cosine is 1/2 at pi thirds, and then again at 5 pi thirds, or I could also call that negative pi thirds. And it's going to keep happening over and over and over again. So it's plus or minus pi thirds plus 2 pi k. Well, this next question over here it already has the inverse there. And so it's saying cosine inverse of a half is what? It's saying whenever it asks you for an inverse question, it's asking you for an angle. I'm going to say that again. Whenever they ask you an inverse question, they're asking for an angle. This case, we would only answer pi thirds because cosine inverse is restricted from here to here. Sine inverse is restricted from here to here, and so is tan inverse. So if that's something we need to talk about in class, I want you to bring this up. For the video right now, we're going to keep moving on. To solve trig functions. To solve trig functions, I have some steps here. For the basic ones that are pretty simple, you're just going to get the trig function by itself and inverse trig both sides or answer the question directly. Sometimes you have to use algebra. I would suggest that you try setting an equation equals 0. Maybe you'll have to use variable substitution. Maybe you'll have to use an identity. Oh, good golly, we might have to factor. Or worst case scenario, maybe even use quadratic formula. The thing about solving trig equations is that sometimes you have to play and you don't always choose the best thing right off the bat. Maybe there is an easier way. You have to try something and see if you can get there. So we're going to do some examples together. The first one. Solve 2 sine of 3x minus the square root of 2 equals 0. This one is actually fairly simple. It's just a plain old sine. The only thing that's sitting there is a sine. That's the only trig function that's there. So what I'm going to do is I'm going to get the sine of 3x all by itself. And to do that, I'm going to move the square root of 2 over to the other side and then divide by 2. So I have the sine of 3x equals the square root of 2 over 2. Now what you might have done in pre-calculus class at this point is that this 3 is bothering me. So I'm going to say let u equal 3x. And in that case, we have sine of u equals the square root of 2 over 2. Why do I like this better? Because I know where sine is the square root of 2 over 2. Just plain sine. I know where sine is equal to the square root of 2 over 2. Where is sine equal to the square root of 2 over 2? It's equal to that at pi fourths. And then again at, let's see, sine, it would be 3 pi fourths. Those two places, sine is a positive square root of 2 over 2. But you see how we solved for u. And u is actually equal to 3x. So to get this, now this is plus 2 pi k, right? Sine's period is 2 pi. So I'm going to divide everything by 3, and I mean everything by 3. So when I solve this, I actually get x is equal to pi fourths divided by 3 is pi twelfths. 3 pi fourths divided by 3 is 3 pi twelfths, which 3 pi twelfths simplifies to pi fourths. And then 2 pi k divided by 3 is 2 pi thirds k. So this was an interesting one. So its solutions are pi twelfths and pi fourths. And instead of happening every 2 pi k, they're happening every 2 pi thirds k, which should make sense to you because you may or may not remember that when the angle is multiplied, your period becomes 2 pi over d, b, I'm not sure what letter they used in pre-calc. And so in this case, the period would be 2 pi over 3. It changed. It's going woo, 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 up and down faster. We changed the period. Okay, the next one. Oh, not so simple. We have sine tan. Oh, there's a typo here. Shame on Miss Newland. There should be an x there. You never write just sine, it's always sine of x. So we have sine x tangent x equals sine of x. I would suggest we try setting this equation equal to 0 by moving the sign over. So now it equals 0, and what I'm going to try doing is factoring, because they both have a sign. If I take a sign out, don't I have tangent of x minus 1 equals 0? All right, now I'm going to talk math to you. I love it when we get to talk math. If I have two equations that are multiplied together and they equal 0, I'm going to use the zero product property, which means I set each factor equal to 0. So this thing times this thing equals 0. What's the only way that two things multiplied together can be 0? One of them, if one of them is 0, that's going to make that statement true. So I set sine of x equal to 0 and tan of x minus 1 equal to 0. Well, where does sine equal 0? Sine equals 0 here and here. So that's 0 and pi and 2 pi and 3 pi and 4 pi. So I'm going to put 0 plus pi k. And where does tan of x equal 1? On the unit circle, tan of x equals 1 there and there. So that's pi fourths and then 5 pi fourths and then again and again and again. So I'm going to also say plus pi k. Okay, those are my answers for that one. Last one. Last one. Well, the good news is I only have one trig function, cosine, but this first one's squared and the next one's not. So I'm going to try setting it equal to 0. Whoops. And now I'm going to try factoring it. And I could use the AC method. I could let u equal cosine of x. So now I have 2u squared plus 3u minus 2. I'm not going to mess with u substitution. I'm just going to go ahead and try to factor it. All right, here we go. I can use guess and check. I know it has to be 2 cosine of x and cosine of x, because cosine times 2 cosine would be 2 cosine squared. I know in order to multiply to be 2, I have to have a 2 and a 1 here. So I know it's either going to be a 2 and a 1, or it could be the 2 here and the 1 here. I'm not quite sure. So what I'm going to do is play with it a little bit. If I distribute and distribute, my outside terms here, if I use this 2, it's going to be 2 times 2 is 4, and then 1, 3. So that's where it's going to come from. So I'm just playing with it a little bit. I know that this has to be a 2 and this has to be a 1 in order to get the 3. And I want the 3 to be positive, so I'm going to put the positive there and the negative there. Woo! All right, if you didn't like that, go factor this and then put your cosine back in. You'll get the same thing. And now I use zero product property again, so I set each factor equal to 0. And I say 2 cosine of x minus 1 equals 0, in which case cosine is 1/2. Where is cosine 1/2 again? It's equal to 1/2 there and there again, so it's plus or minus pi thirds plus 2 pi k. And then the other piece is cosine of x plus 2 equals 0. Where is cosine of x equal to negative 2? It's never equal to negative 2. Remember that cosine just goes up and down 1, negative 1. So that part is out. It's extraneous. All right. Woohoo! That was a fast review of trig. So what should happen now is you should be able to, well, with a little bit of help and references from online and help from Ms. Newland in class and working with your partners and anybody else, maybe asking your parents, maybe going back to your notes from pre-calc last year, hopefully you can now complete that entire, both of the worksheets I've given you, whether it be the AP multiple choice pre-calc stuff you should already know, or if it's the Are You Ready for Calculus worksheet. You got this!